Fixed-wing aircraft. A fixed-wing aircraft uses rigid wings to generate lift as it moves forward through the air. It's the familiar airplane shape: wings, fuselage, tail, and engines. Lift comes from the wing's shape and the forward speed created by engines or propellers. And control surfaces, ailerons, elevators, and rudders, steer and stabilize the aircraft. What makes fixed-wing designs different is their efficiency for sustained flight and range. They turn forward thrust into lift very effectively, which is why commercial airliners and most private planes use this layout. Historically, the Wright brothers' early biplane proved the concept of fixed wings, and incremental advances in materials, aerodynamics, and engines have allowed larger, faster, and safer versions to carry passengers and cargo worldwide. Rotorcraft, helicopters. A rotorcraft generates lift with rotating blades, or rotors, instead of fixed wings, allowing it to hover, take off vertically, and fly slowly or in confined spaces. The rotating disc produces lift by moving air downward, and pilots control motion by tilting the rotor disc and changing blade pitch. What sets helicopters apart is their versatility. They can reach places runways can't, perform search and rescue, and operate from ships in uneven terrain. Their complexity, rotor mechanics, anti-torque systems, and vibration management adds maintenance demands, but that trade-off is what makes them indispensable for many missions. Tiltrotor aircraft. A tiltrotor combines characteristics of both helicopters and fixed-wing planes by using rotors that tilt from vertical for takeoff to horizontal for forward flight. In vertical mode, it behaves like a helicopter, and once the rotors tilt forward, it gains the speed and efficiency of an airplane's wings. This hybrid design addresses the helicopter's speed and range limitations while preserving vertical access. Tilt rotors are mechanically complex and require careful pilot technique, yet they matter because they expand operational flexibility. Military and emerging civilian uses often value that mix of reach and runway independence.
Gliders. Gliders are aircraft without engines that rely on rising air currents and efficient wing design to stay aloft. Pilots launch via tow or winch, then find thermals, ridge lift, or wave lift to gain or maintain altitude. What distinguishes gliders is their extreme aerodynamic efficiency and lightweight structures, which let them travel long distances silently and with minimal energy. They've been part of aviation since the early 20th century and continue as sport, research, and training platforms. Their simplicity also makes them useful for teaching fundamental flight principles. Seaplanes and Floatplanes. Seaplanes and floatplanes are fixed-wing aircraft adapted to operate on water using hulls or floats instead of traditional landing gear. The hull or floats provide buoyancy and allow takeoffs and landings on lakes, rivers, and coastal areas. These designs matter because they open access to remote regions without runways, supporting communities, tourism, and emergency services. The added drag and structural considerations for water operations influence performance, but advances in corrosion-resistant materials and hull design have improved reliability over decades of marine aviation. VTOL, vertical takeoff and landing. VTOL jets are aircraft designed to take off and land vertically like a helicopter, but fly like a jet, often using thrust vectoring engines or dedicated lift fans. They arose from military requirements for short-field operations and shipboard use, with notable examples appearing in the mid-20th century and evolving into modern stealth fighters and experimental craft. What sets VTOL jets apart is their powerful thrust systems and complex balance of lift and control, which demand advanced flight controls and heat-tolerant structures. Their significance lies in tactical flexibility and reduced dependence on runways, though this comes at high cost and engineering challenge. Unmanned aerial vehicles, drones. Drones cover a wide range of aircraft without onboard pilots, from small quadcopters to larger fixed-wing systems, and they fly using remote control or autonomous systems. Multi-rotor drones use several rotating propellers for lift and agility, while unmanned fixed-wing models use wings and forward propulsion for endurance. The defining feature is their remote or autonomous operation, enabling applications in photography, surveying, agriculture, and delivery, plus military uses.
Advances in sensors, batteries, and software have expanded capabilities rapidly, but each type balances payload, range, and control complexity differently. STOL aircraft. STOL stands for Short Takeoff and Landing and refers to planes engineered to operate from very short runways or rough strips. Designers use high-lift wing shapes, powerful engines, and sometimes blowers or flaps to increase lift at low speed, enabling steep climbs and short landings. These aircraft are different because they prioritize low-speed control and ruggedness over cruise efficiency, making them ideal for bush flying, mountain airstrips, and remote air services. Their role has roots in early bush pilots and has continued where infrastructure is limited. Airships and Blimps. Airships and blimps float because they are filled with lighter-than-air gas, like helium, creating buoyant lift rather than aerodynamic lift from wings. Rigid, semi-rigid, and non-rigid designs have been used over the past century for transport, observation, advertising, and scientific work. What differentiates them is the reliance on buoyancy and lower operating speeds, along with large volumes and careful gas management. While their heyday was in the early 20th century, modern materials and safety practices have revived interest for surveillance, advertising, and heavy lift possibilities, where slow, stable flight is advantageous.
Compound helicopters and coaxial designs. Compound helicopters add fixed wings, auxiliary propulsion, or pushers to traditional rotorcraft to increase speed and efficiency, while coaxial helicopters use two counter-rotating rotors stacked on one mast to eliminate the need for a tail rotor. These configurations address helicopter limitations like retreating blade stall, torque losses, and speed caps. The result is greater cruise speed, stability, or payload capacity, depending on the design choices. Their importance shows up in advanced military and commercial projects, seeking faster, more efficient vertical lift solutions without sacrificing VTOL capability. Powered lift and lift fan experimental craft. Powered lift aircraft use engine exhaust or dedicated lift fans to produce vertical lift during takeoff and landing, then transition to wing-borne flight for cruise. Lift fan systems were explored in mid-20th century research and later implemented in modern fighters that require short or vertical operations combined with supersonic capability. These systems are notable for their engineering trade-offs, added weight and complexity versus the ability to operate from confined environments. They matter because they push the boundaries of what aircraft can do, combining runway independence with high-speed performance. Autogyros, gyroplanes. Autogyros generate lift from an unpowered spinning rotor that auto-rotates as the aircraft moves forward, while a separate engine-driven propeller provides thrust. They cannot hover like helicopters, but offer short takeoff and landing capability, stable low-speed flight, and resistance to stalls. Invented in the early 20th century, autogyros were once seen as a bridge between fixed-wing and rotary-wing aircraft. Their simple rotor mechanics and forgiving handling make them useful for sport flying, observation, and niche roles.
Supersonic and high-speed aircraft. Supersonic and high-speed aircraft operate at or above the speed of sound, requiring specialized aerodynamic shapes, heat-resistant materials, and powerful propulsion. They rely on slender, swept wings or delta configurations, and often incorporate area ruling to minimize drag at transonic speeds. The Concorde and various military jets exemplify the trade-offs: exceptional speed and shorter travel times at the cost of fuel efficiency, sonic booms, and stricter operational rules. These types matter for specific missions where speed outweighs the penalties, and research continues into quieter, more efficient designs. Weight shift and ultralight aircraft. Weight shift and ultralight aircraft are minimalistic designs, where pilots shift body weight or move a control bar to change the aircraft's center of gravity and control direction, or fly extremely light fixed-wing craft with simple controls. They are regulated differently in many countries and prioritize simplicity, low cost, and recreational flying. What separates them is the low weight and direct tactile control method, which makes flying accessible and immediate. Composite and advanced material airframes. Modern aircraft increasingly use composite materials like carbon fiber and advanced alloys to reduce weight while increasing strength and corrosion resistance. These materials change how wings, fuselages, and control surfaces are built, allowing more complex shapes and better fuel efficiency. Their significance lies in improved performance, lower operating costs, and longer fatigue life, and they've driven recent advances in commercial and military fleets. The shift from aluminum to composites has been gradual but transformative in aircraft design.
Electric and hybrid electric aircraft. Electric and hybrid electric aircraft use batteries, electric motors, or combinations with conventional engines to provide propulsion, aiming to reduce emissions, noise, and operating costs. Early examples include small trainers, experimental vertical lift prototypes, and commuter concepts. What distinguishes them is the energy source and quieter, simpler propulsion mechanics, though energy density and charging infrastructure remain challenges. Their potential matters for short-haul regional flights, urban air mobility, and as a pathway toward cleaner aviation in the decades ahead.